This is Chapter 12, video assignment number 2, in which we are asked to find the activation energy for a reaction given temperatures and a ratio. So in order to do this, we need to use the Arrhenius equation, which relates temperature to activation energy. And so we have the rate of reaction at 2.2 degrees Celsius is twice that of the reaction at negative 1.1 degrees Celsius. So that gives us the ratio of rate constants, which is K2 over K1, and that equals 2 because it's twice that at 2.2 degrees Celsius rather than at negative 1.1 degrees Celsius. So now we can use the ratio equation of the Arrhenius equation, which is this rate constant equals E to the negative EA over R times the difference in temperatures. So now we need to solve this for activation energy, which we take the natural log of both sides, gives us this, and then in order to get rid of this negative on the activation energy, we can flip the temperatures in here, because this would be a smaller number because it's T2, T1. We can flip it to be T1 minus T2, which lets us take the negative out of the Arrhenius equation. Then we do more algebra, and that eventually gets us down to this. So the equation for activation energy with our given information is EA equals the gas constant times the natural log of K2 over K1, I forgot to write natural log, divided by the difference in temperatures. Now, we have our known values, which is K2 over K1 is 2. We use the gas constant of 8.314 joules per mole Kelvin because we want to end up in joules for the activation energy. And then we have T1 at negative 1.1. We need to change that into Kelvin for units, which gets us T1 being 272.05 Kelvin. Then we do the same thing for T2, and that gets us 275.35 Kelvin. Now we simply substitute these values into the given equation that we solved for earlier, and that gets us an activation energy of a very large number of joules. Then we need to convert that into kilojoules, just because it's an easier number for activation energies. Divide that by 1,000 joules using the conversion factor, and that gets us 188 kilojoules as the activation energy for the reaction. This does have implications for storing fish, because we can see at higher temperatures, the bacterial hydrolysis in fish muscle is quicker than at lower temperatures, which means we need to store fish at lower temperatures in order to slow down the rate of bacterial hydrolysis. In addition, lowering the temperature would also increase the activation energy required for the reaction, which again slows down that reaction as a whole, which means fish spoils less quickly in a cooler environment.